On the evening of October 27, 1992, a 74-year-old physicist died in the back seat of a London taxi. 27 minutes before his heart stopped, he had called his wife from his office at Birkbeck College and told her, quote, "It's tantalizing. I feel I'm on the edge of something," unquote. He had been on that edge for 40 years. His name was David Bohm, and he was, at the moment of his death, the author of the most important set of physics papers of the 20th century that nobody will tell you about. The papers were published on January 15, 1952, in Physical Review, the flagship journal of American physics, volume 85, pages 166 to 193. They solved the deepest unsolved problem in quantum mechanics. They could not be refuted because the mathematics was flawless and the predictions were identical to those of the standard textbook version. And so, in a conference room at the Institute for Advanced Study in Princeton, the director of that institute, a man named J. Robert Oppenheimer, who had been Bohm's doctoral advisor at Berkeley, who had recommended him for his first faculty position, who had certified his classified wartime thesis sight unseen, convened a meeting of the most powerful theoretical physicists in America with the explicit purpose of finding a flaw in the argument. They spent several hours on it. They found nothing. And at the end of the session, according to Bohm's biographer F. David Peat, Oppenheimer looked around the room and delivered the single most damning sentence in the history of modern science. Quote, "If we cannot disprove Bohm, we must agree to ignore him." Unquote. They agreed. Before we dive in, if you want to support the channel and get exclusive content on all things space and physics, check out our Patreon, links in the description. 73 years later, they are still ignoring him. Within weeks of the publication, the United States State Department confiscated Bohm's passport. He had, by that point, already been hauled before the House Un-American Activities Committee, indicted for contempt of Congress, arrested and driven out of Princeton University despite being legally acquitted on every charge. He left for Brazil, lost his American citizenship, and spent the next 40 years in exile, during which time he was never once invited to an American physics conference. The theory he had published in 1952 was declared by professional consensus to be impolite to take seriously. The declaration was never formal. It did not need to be. A generation of graduate students learned, by watching what had happened to Bohm, that working on the foundations of quantum mechanics was the kiss of death for a career. You have probably never heard his name. This is not an accident. It is the point. I need to tell you what his theory says before we go any further, because if you do not understand what Bohm did mathematically, you will not understand why the suppression was so ferocious and so coordinated. The theory says that every particle in the universe has a definite position at every moment in time. It is moving on a specific trajectory. The trajectory is guided by a physically real wave that fills all of space, a wave that obeys the Schrödinger equation and never collapses, never waits for an observer, never cares whether you are looking. Given the initial conditions of the universe and the specific equations Bohm wrote down in 1952, the entire subsequent history of every particle in existence was determined. Determined, not in principle, not metaphorically, as a direct mathematical consequence of the formalism that reproduces every experimental prediction of quantum mechanics to every decimal place. Your body is made of particles. Your brain is made of particles. The thought you're about to have in the next 3 seconds about whether to keep watching this video or to click away, is a pattern of ion flow through the neurons in your cerebral cortex. And those ions in Bohm's formulation have definite positions, and those positions are on trajectories, and those trajectories were fixed before the sun formed. The sense you are having right now of being a conscious agent, weighing the evidence, considering whether this framing is acceptable to you, and arriving at a verdict is the experience from the inside of a trajectory playing out. The verdict has already been reached. You are experiencing the reaching of it. The math does not permit anything else. This is what the physics establishment decided in 1952 to agree to ignore. Not because the math was wrong, because the implications were heavy. And I want you to understand, before we spend 3 hours unpacking how this happened, that what I just described is not some fringe, speculative interpretation. It is the formulation of quantum mechanics that solves the measurement problem, that makes explicit the nonlocality the 2022 Nobel Prize in Physics was awarded for confirming experimentally. That is taught at every serious graduate program in the world. And that, in a survey published in the journal Nature in July of 2025, is identified as the preferred interpretation by 7% of the 1,100 physicists surveyed. 7%. And the number that should disturb you, the number the Nature authors buried in the middle of the paper, rather than leading with it, is that only 24% of those physicists say they actually believe their preferred interpretation is correct. 76% of professional physicists in the year 2005 are telling a survey that they do not believe their own answer to the question of what their most successful physical theory means. They are working with a theory, building careers on it, designing technology around it, and declining to commit to any story about what it is actually describing. This is not skepticism, it is abdication. It is the sound of a discipline that has given up on the question and convinced itself the question was never worth asking. This video is about how that happened. It is about what Bohm actually did in 1952. Because what he did was mathematically beautiful, and it dissolves most of the supposed mysteries of quantum mechanics in about 15 pages. It is about how the theory was suppressed by a coalition of priorities that included institutional self-protection, Cold War paranoia, Copenhagen loyalty bordering on religious conviction, and the personal ambition and cowardice of specific named men who made specific named decisions in specific rooms. And it is about why this matters to you, right now, while you are listening. Because if Bohm was right, and almost every line of evidence suggests he was at minimum possibly right, and at maximum definitely right, then the version of reality the popular physicists have been selling you for 70 years has been a cope. The universe is not fuzzy. The universe does not need you to look at it. The universe is not waiting on your consciousness to make up its mind. The particles in your body have definite positions. Those positions are following trajectories. Those trajectories were set by initial conditions, and those initial conditions were fixed before your parents met, before the Earth formed, before any star in the Milky Way had finished its first rotation. You have been told for most of your adult life that the foundation of physics is strange in a way that is comforting. Look at a particle. The particle decides where to be. Do not look. The particle is a ghost, a probability, a wave. The universe in this telling has a place for you. It is reacting to you. Your consciousness is part of the machinery. That is a bedtime story. Bohm wrote the real 174 years ago. The universe did not wait for you. The universe has never waited for anyone. Every particle has been following a trajectory longer than the age of the stars. Your thoughts are particles following trajectories. Your sense that you are choosing what to believe about this video right now is a pattern of ion flow through neurons. And those ions have had definite positions since before the continents were arranged the way they are. This is not an interpretation. This is what the math actually says in the formulation that solves all the paradoxes. And the physicists who chose the other formulations, the ones that hand-waved about collapse, and observers and complementarity and many worlds, they chose them. And I mean chose, because the implication of Bohm's version was too heavy and too final, and they wanted their universe to stay a little open and a little haunted and a little bit theirs. They lost the argument in 1952. They won the press release. I want to stop here for a moment and make sure the weight of this lands properly. What I am about to walk you through is not a fringe theory. It is published, peer-reviewed, mathematically unassailable physics, developed by a man who was one of J. Robert Oppenheimer's star students at Berkeley, endorsed by Einstein, extended by John Bell, and taught at every serious graduate program in the world today as one of three major interpretations of quantum mechanics. It has simply been declared by professional consensus to be impolite to take seriously. I spent an unreasonable number of hours reading Bohm's original papers, the Pauli correspondence, the HUAC transcripts, the letters from exile, and the material archive at Birkbeck College, where his passport and his papers are now kept. I still do not know how to think about parts of this. I know what the math says. I know what the sociology says. I know the dates and the names and the specific words of dismissal. But every time I sit with what the theory actually means about the nature of the world and about the nature of the mind that is receiving these words, I find something I was not prepared to find. You probably will too. That is why we are going to spend 3 hours on this. We are going to start with a boy in Wilkes-Barre, Pennsylvania in 1917. His father ran a furniture store and told him physics was not a real job. His mother was mentally ill. He read science fiction in the woods because the real world was too lonely. Nothing about his childhood suggested he would grow up to dismantle the philosophical foundation of 20th century physics. But he did, and then they took everything from him for doing it. David Joseph Bohm was born on December 20th, 1917, in Wilkes-Barre, a coal mining town in northeastern Pennsylvania. His father, Samuel Bohm, had arrived from the Hungarian town of Munkacs in what is now western Ukraine. The name on the immigration papers was not Samuel Bohm. It was Shmuel Dum. An official at Ellis Island, impatient with the Yiddish consonants, wrote something else on the line and handed the paper back, and the family name was Bohm from that day forward. Samuel opened a used furniture store on the main street of Wilkes-Barre and built a modest living out of other people's old chairs. He was sarcastic, hard, and unimpressed by abstraction. He told his son more than once that physics was not a real occupation and that the furniture business would be waiting when David was done with his dreaming. David's mother, Frida, née Popke, suffered from what F. David Pete, in his biography of Bohm, describes as manic depression. She was, in Pete's phrase, largely incapable of taking care of her children. The household was run by Bohm's maternal grandmother. Pete describes the home life as chaotic, oppressive, and at times violent. The boy went into the woods. While other children played baseball in the street and formed the packs and cliques that school-age boys form, David walked alone in the trees behind his house. He read science fiction. He discovered the magazine Amazing Stories when he was 10 years old, and the imaginative worlds inside it, with their aliens and their rocket ships and their intergalactic federations, became more real to him than the town he was living in. He wrote his own science fiction stories and mailed them to editors who did not reply. He had vivid, internal fantasies of intense light. Pete describes one of the recurring fantasies as a light that would penetrate matter and probe his own brain. He was, by every account from his own later recollections, a lonely child. He did not have the social reflexes his classmates had. He did not make eye contact easily. He did not know how to banter. He was already the kind of mind that as an adult, Basil Hiley would describe as helical, always circling back to the same questions from higher and higher altitudes. There is one childhood memory Bohm returned to throughout his life. He was walking with friends along a river, and the friends began hopping between rocks, crossing the water by leaping from one stone to the next. Bohm planned each step carefully in advance, looking for the stable stones, calculating the path, and then, somewhere in the middle of the river, he had what he later described as a recognition. Security could lie in movement rather than in fixed positions. The stable configuration was not a place. It was a trajectory. Pete identifies this small childhood moment as the seed of the concept Bohm would, 50 years later, call the hollow movement, the idea that reality is not made of things in positions, but of a flowing, undivided wholeness from which the things and the positions are abstractions. The man who would eventually insist that every particle has a definite trajectory learned to trust trajectories over rocks while he was still in short pants. He went to Pennsylvania State College, then to Caltech for graduate work. Then, in 1941, he transferred to the University of California, Berkeley, to work under a young theorist named J. Robert Oppenheimer. Oppenheimer was, at the time, already a legend among Berkeley's theoretical physics students. He had studied with Max Born in Germany, worked with Ehrenfest in Leiden, been tutored by Pauli, and returned to the United States to build, almost single-handedly, the first serious school of theoretical physics on the West Coast. His Berkeley group was intense, brilliant, and a little cultish. Oppenheimer had favorites. He was cutting with those he did not favor. He was a lightning rod for gifted students who wanted to be in the orbit of a mind that seemed to move faster than their own. Bohm adored him. In a 1979 interview with the historian Martin Sherwin, recorded decades after everything had fallen apart between them, Bohm said of Oppenheimer, quote, "He helped me to get into Berkeley, and he helped me to get to Brazil. I can't blame him for not liking what I'm doing. I think he acted fairly to me, as far as he was able to," unquote. That is the last line. As far as he was able to. And we will come back to it, because it is doing a lot of work. Bohm, at the time of that interview, knew exactly how much Oppenheimer had done and exactly how much he had failed to do, and he was still trying to be generous. At Berkeley, Bohm wrote his doctoral thesis on the scattering of protons and deuterons. The work was completed in 1943. By then, the United States was at war, and Berkeley's radiation laboratory had become one of the primary sites of the Manhattan Project, and Oppenheimer was already at Los Alamos, running the bomb. Bohm's thesis results were immediately classified. He was not allowed to see his own completed work. General Leslie Groves, the Army officer in charge of Manhattan Project security, denied Bohm a clearance because of his left-wing political associations, and the refusal was absolute. Pete records the absurd situation in his biography. Bohm, he writes, was not only barred from defending his thesis, he was not even allowed to write his own thesis in the first place. Oppenheimer had to intervene directly, writing to Berkeley to certify that Bohm had in fact completed satisfactory doctoral research, without being able to describe what that research consisted of. The university awarded the degree on Oppenheimer's word. Bohm became a doctor of physics without being allowed to read his own dissertation. Think about that for a moment. I am telling you this not because it is interesting background, but because it connects directly to what the United States government did to Bohm 10 years later. In 1943, the state classified his intellect and rented it back to him on terms. In 1951, the same state would look at that intellect again and decide that on reconsideration, it was dangerous, and it would unmake the arrangement. The man who was not cleared to read his own thesis would become the man who was not cleared to leave the hemisphere. Bohm was a member of the Communist Party of the United States of America. He joined in 1942. Membership lasted approximately 9 months. His own account, given years later to Martin Sherwin, was that he became disillusioned quickly. Quote, "I began to feel that they did nothing but talk about things of no significance, about trying to organize protests of affairs on the campus. The meetings were interminable." Unquote. That is the official recollection. What is also true is that at Berkeley in the early 1940s, a constellation of young left-wing scientists orbited around a loose Communist Party study group. Giovanni Rossi Lomanitz, Joseph Weinberg, Max Friedman, Bernard Peters, David Hawkins. They argued about dialectical materialism. They organized campus protests against the internment of Japanese Americans. They believed, as many intelligent young people in the Depression era believed, that capitalism had failed and that a planned economy was the obvious next step in human history. Bohm, in this period, also had a romantic relationship with Betty Friedan, who would go on to write The Feminine Mystique and to ignite the second wave of American feminism. The Berkeley radical scene was small and concentrated. Everyone knew everyone, and the FBI, through wiretaps placed on a local party functionary named Steve Nelson, knew them all too. After the war, Oppenheimer returned from Los Alamos, a national hero. In 1946, he was on the cover of Time magazine. In 1947, he became director of the Institute for Advanced Study in Princeton, which had been Einstein's refuge since 1933, and which was, at that point, the single most prestigious theoretical physics post in the world. Bohm, meanwhile, had taken an assistant professorship at Princeton University, the separate institution across town. Henry DeWolf Smith, chairman of Princeton's physics department, wrote when he recruited Bohm that, quote, "Bohm has been recommended to us as one of the ablest young theoretical physicists that Oppenheimer has turned out." Unquote. The mentor's reflected glow was still doing work. Bohm arrived in Princeton in January of 1947. He was 29 years old. He was, by every account of the period, a rising star. And this is where the texture of the story begins to take on the quality of tragedy, because Bohm in this period was doing some of the best work of his life, and he was doing it inside the interpretational framework he would, within 5 years, tear down. He wrote, between 1947 and 1950, a textbook on quantum mechanics. It was published by Prentice Hall in 1951. The title was simply Quantum Theory, And here is the thing that you need to understand about this book. It is, by essentially universal agreement among people who have read it, the single, clearest, most careful, most honest exposition of the Copenhagen interpretation of quantum mechanics ever written. Bohm in 1951 was a Copenhagen loyalist. He believed, as Niels Bohr and Werner Heisenberg had insisted since the mid-1920s, that the wave function was not a physically real thing, but a compact description of the statistical outcomes of measurement. He believed that particles did not have definite positions until an observation created the answer. He believed that quantum mechanics was the end of the story, that the causal classical worldview was finished, that asking what was really going on underneath the formalism was a kind of philosophical nostalgia that serious physicists had outgrown. His book walks the reader through all of this with extraordinary care. He presents the double-slit experiment, the uncertainty principle, the collapse of the wave function, the complementarity of wave and particle descriptions. He presents them so cleanly that the book became, and remained for decades, one of the standard graduate textbooks in the English-speaking world. And then he did something that almost no one does, which is that he sent a copy to Albert Einstein. Einstein was, at that point, 4 years from death, and deep into his final phase of semi-public isolation at the Institute for Advanced Study. He had spent the previous 25 years refusing to accept the Copenhagen interpretation. The famous line about God not playing dice was already old. The 1935 paper with Podolsky and Rosen, which purported to show that the quantum description was incomplete, was 16 years old. Einstein was not a fringe figure. He was the most famous living scientist in the world. He was also, in the private opinion of most of the young physicists coming up through the 50s, a relic, a man whose time had passed, a romantic, unable to accept the new physics because it violated his classical intuitions. He had become, at Princeton, the elderly uncle of quantum mechanics, loved but no longer listened to. Einstein read Bohm's textbook. According to a Physics Today review of the history, Einstein then called Bohm and said that he had never seen the Copenhagen interpretation presented so clearly. And then he told Bohm that he did not believe a word of it, and he spent the afternoon explaining to the 33-year-old assistant professor why the clearest presentation of a philosophical position was not the same thing as a correct philosophical position. What they said to each other is not recorded in full. What is recorded is that Bohm came out of that conversation changed. He told Basil Hiley later that Einstein had, in that single conversation, dismantled in him a faith he had not realized he was holding. Einstein had not given him an alternative theory. He had simply refused to accept the Copenhagen account, and had pressed, with the patient rigor of a man who had spent half a century thinking about exactly this, on every place where the account did not hang together. Why does the wave function collapse? What triggers the collapse? At what scale? How is it that the same mathematics is supposed to describe both a deterministic evolution and a random jump, with the dividing line placed wherever the experimenter finds it convenient to place it? What is a measurement? What is an observer? Why is any of this principled rather than a bookkeeping convenience? Einstein was not asking these questions to score points. He was asking them because he actually wanted to know. This is where the story of the 1952 papers begins. Einstein's criticism catalyzed Bohm. He began writing immediately. The paper was substantially drafted by the summer of 1951. By July of that year, it was submitted to physical review. The peer review was benign. The paper was accepted for publication, and the issue was scheduled for January of 1952. In the intervening months, Bohm's life was going to end, in a very real sense, and a different and much smaller life was going to take its place. The paper would arrive in print on the same continent as its author only because the issue of physical review was printed in the United States. Bohm, by the time the publication date arrived, would be 3,000 miles away, in a country whose language he did not speak, holding a passport that was no longer his. But before we get there, we need to slow down. We need to walk through what the paper actually says, because everything that happens after 1952 makes sense only if you understand what was in those pages. What Bohm did, mathematically, was beautiful. What he did, ontologically, was revolutionary. And what he did, sociologically, was unforgivable, because he pulled back the curtain on a discipline that had convinced itself there was no curtain to pull back. Here is the move in one sentence, and then we will slow down and really look at it. Bohm took the Schrödinger equation, the same equation every physics student memorizes, and he rewrote the wave function in what is called polar form. That is it. That is the entire mathematical innovation. Everything else flows from that one rewriting. Let me walk you through it. The Schrödinger equation is the fundamental equation of quantum mechanics. It describes how the wave function of a system evolves through time. The wave function is usually written as the Greek letter psi, and in the standard textbook treatment, it is a complex valued quantity, which means it has both a real and an imaginary part. Bohm wrote it differently. He wrote psi as a single amplitude r multiplied by a pure phase, where the phase is the exponential of I times s divided by h bar. Two real quantities, r, which is the amplitude of the wave, s, which is the phase. Both are just ordinary real numbers at every point in space and time. You can do this. It is a mathematical identity. Any complex number can be written this way. There is no physics in the rewriting itself. Schrödinger knew this. Every textbook acknowledges it in passing. Now here is what happens when you substitute that form back into the Schrödinger equation and separate the real and imaginary parts. You get two equations. One of them is the continuity equation, which describes how probability flows. That equation is familiar and uncontroversial. Everyone who has taken a graduate course in quantum mechanics has seen it. The second equation, the one nobody wanted to look at, is a modified Hamilton-Jacobi equation. The Hamilton-Jacobi equation, for context, is the most elegant formulation of classical mechanics. It describes how a classical particle moves under the influence of a potential, with the phase S playing the role of the classical action. Every mechanics student learns it. It is the bridge between classical physics and more advanced formulations. And what Bohm showed was that when you do the polar decomposition of the Schrödinger equation, the second equation you get is exactly the classical Hamilton-Jacobi equation, with one extra term added. One extra term. A single additional quantity sitting on the right-hand side, appearing out of the mathematics without anyone having put it there by hand. Bohm called that term the quantum potential. The symbol for it is Q. The quantum potential, written out, is negative h bar squared over 2m times the Laplacian of r divided by r. What this means in physical terms is that there exists a new kind of potential energy in nature. It is not the electromagnetic potential. It is not the gravitational potential. It is not the strong or weak nuclear force. It is a potential that depends on the shape of the wave function itself, on how the amplitude r is curved in space, and it produces forces on particles, real forces, forces that push the particles around. The guiding equation, which Bohm derived from the same rewriting, says that each particle has a velocity equal to the gradient of s divided by the mass. In plain English, every particle is being pushed around by the phase of its own wave function, and that phase is being sculpted by the quantum potential which responds to the global configuration of the experiment. I need to stop here, because the implication of what I just said is the entire ballgame. In standard quantum mechanics, particles do not have positions and trajectories between measurements. The wave function tells you the probability of finding a particle at a given location if you measure, and that is the complete story. Ask where the electron is in an unobserved hydrogen atom, and the textbook answer is that the question has no meaning. In Bohm's formulation, that is false. The particle has a position. It always had a position. It has a velocity given by a specific equation. It is moving on a specific trajectory. The wave function is also real. It is a physically existing field. It spreads out across space and interferes with itself, and its job is to guide the particle along its path. The particle is like a surfer. The wave function is the ocean. The ocean is real, and the surfer is real, and the surfer is being carried by the ocean. And if you know where the surfer started and what the ocean is doing, the surfer's future is determined. Let me give you the specific case everyone knows. The double-slit experiment. You have a source that emits particles one at a time. You have a barrier with two narrow slits, and you have a screen behind the barrier that records where each particle lands. In the Copenhagen version, which is what you were taught, the particle leaves the source, and until it hits the screen, it does not have a definite position. It exists as a spread-out wave of probability. The wave passes through both slits simultaneously, because a probability wave can do that. The two halves of the wave interfere with each other on the far side of the barrier, creating regions where the probability is high and regions where it is low. When the particle finally hits the screen and is detected, its position randomly resolves somewhere in the probability distribution. And after many particles, you see the interference pattern build up dot by dot on the screen. You have probably heard this story. You have probably watched a YouTube video in which a bearded British professor says that the electron went through both slits at once, and that this is one of the great weird truths of quantum reality, and that you must simply accept it. Here is what Bohm's version says. The particle leaves the source. It has a definite position. It is going to go through exactly one of the two slits, like a classical object would. The wave function, which is a real physical field, also leaves the source. The wave function is the thing that goes through both slits. The wave function interferes with itself on the far side, creating a pattern of peaks and troughs in the quantum potential. The particle, which is going through one of the slits, feels the quantum potential. The quantum potential steers it. It steers it toward regions of constructive interference and away from regions of destructive interference. So the particle ends up tracing a curved, deterministic path from the slit through the interference region onto a specific spot on the screen. The spot is determined entirely by two things: the exact position of the particle when it left the source, and the exact shape of the wave function. If you knew both of those with infinite precision, you could predict with certainty where that specific particle would land. In practice, you cannot know the initial position with infinite precision, so you see statistical outcomes. But the statistics emerge from hidden but completely determined initial conditions. The universe is not rolling dice. The universe is running the trajectory. The dice are in your ignorance. In 1979, 3 physicists, Chris Philippidis, Chris Dewdney, and Basil Hiley, sat down and computed the Bohmian trajectories for the double-slit experiment for the first time. They published the result. The trajectories, when plotted, form a beautiful, smooth, non-crossing pattern. The particles coming out of one slit curve toward the high probability regions of the interference pattern on the screen. The particles coming out of the other slit do the mirror image. The 2 streams of trajectories never cross, which is a consequence of the guiding equation. And together they reproduce the interference pattern exactly. When you look at the plots, you can see for yourself that the particles went through one slit. The picture has been in the literature for 46 years. It is in no textbook that most physics undergraduates will ever open. The particles have trajectories. The trajectories are real. We can compute them, we can draw them. They match the data, and you were taught by people with doctorates that particles do not have trajectories because the particles do not have trajectory story is more comforting than the answer, which is that the particles have trajectories and that the trajectories were already fixed before you started the experiment. And here is where it gets worse. The quantum potential, unlike every other potential in physics, does not fall off with distance. This is the technical detail that more than anything else in Bohm's papers made Einstein uncomfortable, made Heisenberg dismissive, and made Bell realize that the whole of quantum foundations was going to have to be rewritten. The gravitational potential between 2 masses weakens as you move them apart. The electrical potential between 2 charges weakens as you move them apart. Every classical potential weakens with distance. The quantum potential does not. The quantum potential depends on the shape of the wave function, specifically on its curvature, and the shape of the wave function is whatever the global configuration of the experiment makes it, instantaneously everywhere in space. If you move a slit in the barrier, or if you put a detector somewhere on the far side of the apparatus, the quantum potential changes everywhere, instantly. The particle, which is following the gradient of the phase S, feels that change instantly. This is non-locality, written in equations, mathematically explicit, unavoidable, fundamental. What this means is that Bohm's theory is not merely compatible with entanglement. Bohm's theory predicts the non-local correlations of entangled particles as a direct mathematical consequence of the guiding equation. When you have 2 entangled particles separated by 1,000,000 miles, and you do something to one of them, the wave function of the pair changes instantaneously. The quantum potential changes instantaneously. The guiding equation for the second particle immediately incorporates that change, and the second particle's subsequent trajectory reflects it. There is no faster than light signaling because you cannot control which outcome you get, only the statistics. But the dependence is there. It is explicit. It is real. And this is the exact feature that John Bell would, 12 years later, prove is required of any theory that reproduces the experimental predictions of quantum mechanics. Bell did not invent non-locality. He proved that non-locality is the price of admission to quantum reality. Bohm simply built the theory that paid that price up front, honestly, in ink. Let me say this clearly, because the philosophical literature is full of evasions and I am tired of them. The universe is non-local. This is not an interpretive claim. This is an experimental fact. The Bell inequality experiments, starting with John Clauser and Stuart Friedman in 1972, continuing through Alan Aspect in 1982, through to the loophole-free experiments of 2015, have confirmed to something like 30 standard deviations that the world violates the Bell inequalities in exactly the way quantum mechanics predicts. No local hidden variable theory can reproduce the data. This is the consensus finding of 70 years of experimental physics. It won the Nobel Prize in 2002. The universe is non-local. When two particles are entangled and you measure one, something about the other is immediately settled across arbitrary distances by some connection that is not mediated by anything traveling through space at less than the speed of light. Standard quantum mechanics, the Copenhagen version, deals with this by refusing to describe it. The wave function collapses, we say, but we do not say what that means. We do not say what causes it. We do not say how fast it happens. We do not say what the metaphysical status of the two particles is between the measurements. We just write down the rule and move on. Bohm's theory deals with it by saying, yes, non-locality is real. Here is the equation. The quantum potential connects distant particles instantaneously. This is how the world actually works. And if that bothers you, it should, because the world is in fact a much stranger place than the classical one we thought we were living in. The measurement problem, which is the central unsolved problem of quantum foundations, simply does not exist in Bohm's theory. Let me walk you through why. In Copenhagen quantum mechanics, there are two different rules for how the wave function evolves. One rule is the Schrödinger equation, which is smooth, deterministic, continuous, and describes what happens between measurements. The other rule is the collapse postulate, which is sudden, random, discontinuous, and describes what happens during a measurement. There are two rules, not one, and the rules contradict each other. The Schrödinger equation is unitary, which means probabilities are conserved. Collapse is not unitary, which means probabilities are not conserved. These two processes cannot be two facets of the same underlying dynamics. They are two different laws of physics, and the theory is silent on what determines which law applies at any given moment. When does Schrödinger evolution end and collapse begin? What is a measurement? What qualifies as an observer? The theory has no answer. Every serious physicist knows this. Most of them have decided to not think about it. In Bohm's theory, there is only one rule. The wave function always evolves according to the Schrödinger equation. Always. No exceptions. The particles always follow the guiding equation. Always. No exceptions. When an experimenter performs a measurement, what actually happens in Bohm's formulation is that the measuring apparatus is itself described by a wave function, which becomes entangled with the wave function of the system being measured. The combined wave function on the joint configuration space of system plus apparatus evolves into a superposition of different branches. Each branch corresponds to a different possible outcome of the measurement. The actual particles, including the particles that make up the apparatus, are somewhere definite. They are in one of the branches. The other branches are real. They continue to exist as part of the wave function, but the particles are not in them. And because the branches become rapidly decoupled from each other through interactions with the environment, a process we now call decoherence, the branches where the particles are not, become, for all practical purposes, invisible and inert. There is no collapse. The other branches do not vanish. They just cease to be relevant to the branch the particles are in. The appearance of collapse is produced by the behavior of the particles, not by a separate physical process. Bohm wrote down the first serious description of decoherence in his 1952 paper. 1952. H. Dieter Zär would not rediscover decoherence and make it a fashionable topic in quantum foundations until 1970. Wojciech Zurek would not popularize it until the 1980s. Between Bohm and Zär, a period of 18 years, the solution to the measurement problem was sitting in plain view in an already published paper, and the people who could have used it were not allowed by the sociology of their discipline to cite it. I want to pause here and make sure you are still with me, because we just covered a lot of ground, and I do not want the weight of what we just did to get lost in approximately 15 pages of mathematics. In a paper submitted from Princeton and published in Exile, David Bohm solved the measurement problem. He did it by treating the wave function as a physically real guiding field, and by giving particles definite positions at all times. He produced a theory that reproduces every prediction of standard quantum mechanics, eliminates the need for two different dynamical laws, dissolves the observer question, explains decoherence 18 years before decoherence became a research topic, and makes explicit the non-locality that Bell would, a dozen years later, prove is unavoidable. The theory was logically consistent. The theory was mathematically rigorous. The theory was empirically adequate. The theory is still all of those things today. And in the opinion of 76% of currently practicing physicists, it is not a theory their community has decided to take seriously. There is a reason. The reason is that the theory implies something people do not want to hear. It implies determinism. In Bohm's universe, every particle has a definite position and a definite velocity at every moment. And the future evolution of every particle is completely determined by two things: the wave function, which evolves deterministically through the Schrödinger equation, and the initial positions of the particles, which were set at some moment in the past. Given these two things, the entire subsequent history of the universe is fixed. You could, in principle, compute it forward. You cannot in practice, because you cannot know the initial positions with infinite precision. And because the quantum equilibrium condition shows that the statistical behavior of typical subsystems perfectly mimics the probabilistic predictions of standard quantum mechanics, but the ignorance is on your end. The universe itself is running a trajectory, one trajectory, the same trajectory it has been running since whatever initial condition set the wave function and the particle positions at the beginning of time. Your body is made of particles. Your brain is made of particles. The ions moving through the sodium and potassium channels in your neurons right now, as you listen to these words, are particles. In the Bohmian picture, those particles have definite positions and velocities. They are being guided by the global wave function of everything, and the trajectory they are on was fixed by initial conditions set before the Earth formed. The thought you are about to have in 3 seconds about what I just said is a trajectory already determined. Your sense that you are considering this claim and deciding whether to believe it is a pattern of particle motion, and the pattern has already been set. The decision is not being made. The decision is being played back. I want you to sit with that for a moment before we move on. because the physics community sat with that in 1952 and they did not like how it felt, and they decided, collectively, without a formal vote, to pretend the papers had not been published. To understand why the physics community was prepared to pretend a set of published papers did not exist, you have to understand how they had arrived at the certainty that such papers were impossible in the first place. And to understand that, you have to go back 20 years to 1932 and to a book that was, for an entire generation of physicists, something like a sacred text. The book was called Mathematische Grundlagen der Quantenmechanik, the mathematical foundations of quantum mechanics. The author was John von Neumann. Von Neumann, in 1932, was 29 years old and already a legend. He had reformulated quantum mechanics in the language of Hilbert spaces and linear operators, a formulation that is still, today, the mathematical backbone of the entire subject. His book was rigorous, comprehensive, and written in a style of assured finality that brooked no disagreement. And on page 325 of the English translation, in the context of a chapter on measurement, von Neumann included a mathematical theorem that he claimed demonstrated the impossibility of what would come to be called hidden variable theories. The claim was this: any attempt to supplement quantum mechanics with additional variables, with hidden parameters that would restore classical determinism and fix the values of quantities prior to measurement, would lead to predictions different from those of standard quantum mechanics. Since standard quantum mechanics had been empirically verified, such hidden variable theories had to be wrong. Von Neumann wrote, and this is the exact translation that appeared in the 1955 English edition from Princeton University Press, quote, "It is therefore not, as is often assumed, a question of a reinterpretation of quantum mechanics. The present system of quantum mechanics would have to be objectively false in order that another description of the elementary processes than the statistical one be possible." Unquote. In plain English, he said you cannot add hidden variables to quantum mechanics. If hidden variables are possible, quantum mechanics is false. Quantum mechanics is true. Therefore, hidden variables are impossible. Quod erat demonstrandum. The theorem was accepted. It was taught in graduate courses. Max Born, in his 1949 book, Natural Philosophy of Cause and Chance, stated the conclusion flatly, quote, "No concealed parameters can be introduced with the help of which the indeterministic description could be transformed into a deterministic one." Unquote. A whole generation of physicists learned that the question of whether quantum mechanics might be underwritten by some deeper deterministic theory had been mathematically closed in 1932. The issue was dead. To pursue it was to mark yourself as someone who did not understand the mathematics, someone stuck in pre-quantum thinking, someone who would not accept the genuine novelty of 20th century physics. The theorem was the emperor's clothes. Nobody looked too closely, because not looking too closely was a professional requirement. There was one person who looked closely. Her name was Greta Hermann. She was a German mathematician and philosopher, a student of the great Göttingen number theorist Emmy Noether. She was born in 1901, which means that by 1935, when the story I am about to tell you starts, she was 34 years old and one of the most gifted young philosophers of science in Europe. She had spent time at the Institute for Theoretical Physics in Leipzig under Werner Heisenberg. She had corresponded with Bohr. She understood quantum mechanics at a depth most physicists of her generation did not. And she read von Neumann's proof. She found the flaw within what appears to have been a few weeks. The flaw, if you have the mathematical background, is mortifyingly simple. Von Neumann's proof depended on an assumption he called the additivity of expectation values. He assumed that the average value of a sum of observables must equal the sum of the average values of those observables, and that this must hold for all observables, including observables that do not commute with each other. That assumption for commuting observables is fine. That assumption for non-commuting observables is physically meaningless, because for non-commuting observables, the sum is not even operationally defined. You cannot measure the sum of two non-commuting observables by measuring each of them separately and adding, because the act of measuring one of them changes the system in a way that affects the measurement of the other. Von Neumann assumed the additivity anyway. He then derived from that assumption the conclusion that no hidden variable assignment could reproduce the quantum expectation values, and he presented this as a proof that hidden variables were impossible. What he had actually proven was that hidden variables that obeyed an unphysical additivity condition were impossible. He had assumed, in the premise of his theorem, that the hidden variables had to satisfy a condition that no serious hidden variable theorist would ever have proposed. The theorem was vacuous. It was a circular argument dressed up in mathematical notation. It proved what it assumed, and nothing more. Hermann wrote this up. Her paper was titled Die naturphilosophischen Grundlagen der Quantenmechanik, the natural philosophical foundations of quantum mechanics. She published it in 1935 in a journal called Abhandlungen der Frisian Schule, the Proceedings of the Frisian School, a neo-Kantian philosophical publication that had approximately the circulation and influence you would expect for a journal with that name. She had chosen the outlet, in part, because it was a journal she knew would publish her, and in part because her own philosophical framework was Kantian, and the Frisian school was the natural institutional home for that approach. She had also, earlier, in 1933, circulated an unpublished manuscript to Paul Dirac, to Werner Heisenberg, and to Niels Bohr. She had sent her arguments to the three most important living physicists on the continent. They did not respond. They did not engage. They did not cite her. The paper in the Frisian Proceedings vanished into the academic silence that swallows papers published in the wrong journals by women philosophers working in unfashionable traditions. By 1936, Hermann was in exile from Nazi Germany, having fled to Denmark, then France, then London, where she spent the war years teaching at a secondary school. When she finally returned to German academia after the war, she went into philosophy of science rather than physics proper. Her 1935 paper, which had identified one of the most consequential errors in the history of 20th century physics, remained essentially unknown to the physics community until Max Jammer rediscovered it in his 1974 book, The Philosophy of Quantum Mechanics. Let me tell you what this means in the plainest language I can find. The paper was published in 1935. The correct answer to the most important structural question in the foundations of quantum mechanics, which was whether hidden variable theories were possible, had been worked out and put in print. For the next 31 years, physicists continued to cite von Neumann's proof as establishing the impossibility of hidden variables. They taught it to graduate students. They used it to dismiss anyone who asked foundational questions. They built careers on top of it, and the whole time the refutation was sitting in a dusty Kantian journal, unread by the community that most needed to read it, because the author was a woman, because the journal was philosophical rather than physical, and because the conclusion was simply not what anyone wanted to believe. David Bohm, the Cornell theorist, wrote about this episode in 1993 in a paper in Reviews of Modern Physics, and his tone is the tone of a man who has finally given up on being polite. Quote, "A few years later, Greta Hermann, 1935, pointed out a glaring deficiency in the argument, but she seems to have been entirely ignored. Everybody continued to cite the von Neumann proof. A third of a century passed before John Bell, 1966, rediscovered the fact that von Neumann's no hidden variables proof was based on an assumption that can only be described as silly. So silly, in fact, that one is led to wonder whether the proof was ever studied by either the students or those who appealed to it to rescue them from speculative adventures." Unquote. So silly, Bohm wrote, that one wonders whether any of them ever actually read it. And that is, I think, probably the honest answer. The proof was cited because citing it settled the argument. The argument being settled was what mattered. The proof was the object you pointed to in order to avoid having the conversation. This is the intellectual environment Bohm's papers landed in 1952. A generation of physicists had spent 20 years confident that hidden variables were mathematically impossible. And now, an assistant professor in Princeton, who was not even a senior figure, had published in the discipline's flagship American journal a fully worked out hidden variable theory that reproduced all the predictions of standard quantum mechanics. The theory that could not exist, according to the theorem every graduate student was told to revere, had just existed. Physical Review had printed it. You could go to the library and hold it. The response was, to put it carefully, ugly. Werner Heisenberg, writing in a 1955 essay in a Pauli Festschrift, dismissed Bohm's theory as, quote, an ideological superstructure which has little to do with immediate physical reality, unquote. He added, with a kind of aggrieved, theological tone, that, quote, such attempts are always distressing, for they mislead us into continually occupying ourselves with the inevitable cracks in the old bottles, instead of rejoicing over the new wine, unquote. In the same essay, Heisenberg coined the very term Copenhagen interpretation, which had not previously been in common use. Don Howard, the philosopher of science, has documented that until Heisenberg invented the phrase in 1955, there was no unitary entity called the Copenhagen interpretation. Bohr, Heisenberg, Born, and Pauli had all held somewhat different views on what quantum mechanics meant, and they had disagreed with each other in substantial ways during the 1920s and 30s. Heisenberg, in response to Bohm, unified these disagreements into a single, coherent-sounding brand in order to have a thing to rally around. The Copenhagen interpretation, as a definite article as the thing you learn in graduate school, was invented retroactively in 1955 as a defensive rhetorical move against Bohm. Wolfgang Pauli, who had been Einstein's greatest living opponent in the foundational debates of the 1930s, was more contemptuous. He wrote to his colleague Marcus Fiers on January 10, 1952, exactly 5 days before the papers were published, quote, Die Sache von Bohm ist beinahe ein Plagiat. The Bohm thing is almost plagiarism, unquote. He was referring to the fact that de Broglie had proposed a similar pilot wave theory in 1927, which Pauli himself had attacked at the Solvay conference that year, and which, de Broglie had abandoned in response. In a letter to Leon Rosenfeld on March 16, 1952, Pauli called Bohm's theory, quote, a revival of de Broglie's old errors of 1927, unquote. He wrote, in the same letter, that he was worried about Bohm's influence on, quote, the younger fellow travelers of Bohm, mostly deterministic fanaticists, more or less Marxistically colored, unquote. You should hear that sentence the way it was meant to be heard. Pauli was writing in 1952, in the first year of the McCarthy era, and he was labeling deterministic physics as the intellectual property of communist fellow travelers. He was making the political and the scientific into the same charge. In a letter to Max Born in December of 1954, Pauli would go further, quote, contrary to all reactionary efforts, Bohm, Schrödinger, and so on, and in a certain sense also Einstein, I am certain that the statistical character of the psi function will determine the style of the laws for at least a few centuries. To dream of a way back to the classical style of Newton-Maxwell, seems to me without hope, devious, of bad taste. And, we may add, it is not even a good dream, unquote. Devious, of bad taste. A man had written a paper. Pauli was calling the paper a moral failure. Leon Rosenfeld, who was Bohr's closest intellectual ally in Copenhagen, and perhaps the most loyal defender of the Bohr orthodoxy, went even further. In a letter to Pauli on March 16th of 1952, Rosenfeld wrote, quote, I hope that the people who told you that I was interested in Bohm's heresy did not suggest that I was in any way impressed by it. I am only interested in stamping out this new obscurantism because it is positively harmful, unquote. Heresy, stamping out obscurantism. This is not the vocabulary of scientific disagreement. This is the vocabulary of religious persecution. Rosenfeld wrote directly to Bohm in May of 1952 and told him, quote, I certainly shall not enter into any controversy with you or anybody else on the subject of complementarity for the simple reason that there is not the slightest controversial point about it, unquote. Complementarity, the central doctrine of the Bohr school, the idea that particles and waves are mutually exclusive aspects of quantum reality that cannot be jointly realized, was being defended by Rosenfeld not as a theory open to criticism, but as a truth that had been settled and that further discussion of was in itself illegitimate. When John Bell, a decade later, wrote to Rosenfeld asking for engagement with the question of hidden variables, Rosenfeld replied, in a letter in December of 1966, that Bell was wasting his talent, a waste of his talent, on the questions that would win the 2022 Nobel Prize in Physics for experimental tests of the predictions nobody in Copenhagen had wanted to test. Niels Bohr himself, the founder of the Copenhagen interpretation and the single most influential figure in mid-20th century physics, called Bohm's theory, in a private remark relayed by colleagues, quote, very foolish, unquote. Einstein, who might have been expected to welcome the theory, given his lifelong opposition to the Copenhagen orthodoxy, wrote to Max Born in May of 1952 and said, quote, have you noticed that Bohm believes, as de Broglie did by the way 25 years ago, that he is able to interpret the quantum theory in deterministic terms? That way seems too cheap to me, unquote. Too cheap. Einstein's objection was not to determinism. Einstein adored determinism. Einstein's objection was to the explicit non-locality of the theory. Einstein wanted a theory that was both deterministic and local, the kind of theory Bell would prove in 1964 was impossible. In other words, Einstein had correctly identified the feature of Bohm's theory that Bell would later prove was required of any hidden variable theory whatsoever. Einstein rejected Bohm for possessing the exact feature that nature in fact requires. This is a tragedy of its own kind, and we will come back to it. And then there is Oppenheimer. Oppenheimer, who had been Bohm's doctoral advisor, who had written the letter that got Bohm into Princeton, who had benefited for years from Bohm's brilliance and loyalty, convened the meeting at the Institute for Advanced Study, at which the famous line was spoken. According to Pete's biography, Oppenheimer gathered a group of physicists at the Institute with the purpose of finding a flaw in Bohm's papers. They spent hours going through the arguments. They could not find a flaw. And at the end, Oppenheimer, frustrated, said, quote, "If we cannot disprove Bohm, we must agree to ignore him," unquote. I want you to hear the verb in that sentence. Agree, not decide, not conclude. Agree. A group of men gathered in a room at one of the most prestigious research institutions in the world were asked to enter into a compact of collective silence regarding a set of papers they could not refute. And they did. That is, by a comfortable margin, the most remarkable sentence in the history of 20th century physics. And you probably have never heard it before. Oppenheimer also used a different phrase, one that is better attested in the historical record. He called Bohm's work juvenile deviationism. This phrase is confirmed in the 2024 book Quantum Drama by Jim Baggott and John Heilbronn, as well as in earlier sources. Juvenile deviationism is a specific piece of vocabulary. It comes directly from the Stalinist Party disciplinary language of the 1930s and 40s, where it was used to describe young communists who had strayed from the correct party line. You do not use that phrase about a scientific paper by accident. You use it because you want your listener to hear the political resonance. You use it to signal that this physics, authored by this person who has just been before HUAC, carries a whiff of the same ideological contamination. Oppenheimer, who had himself cooperated with HUAC in 1949 by naming former students, was deploying the security state's vocabulary against a student he had mentored in order to stigmatize a paper that had just been peer-reviewed and accepted by the American Physical Society. The physical sciences are supposed to be above this kind of thing. They are not. They never were. They were above it only because we were not looking. The pattern, by 1952, was set. Pauli, disdainful. Heisenberg, contemptuous. Rosenfeld, inquisitorial. Bohr, dismissive. Einstein, skeptical, but for the wrong reason. Oppenheimer, treacherous. Born, who might have been the most sympathetic elder statesman, caught between his affection for Einstein and his loyalty to the orthodoxy, mostly silent. And the young physicists coming up through the field, the ones whose careers were still being built, looked at this chorus and drew the correct professional conclusion. They stopped citing Bohm. They stopped reading him. They learned, by observing what had happened to one of the most promising theorists of their generation, that taking the measurement problem seriously was career suicide. There is one exception, a young philosopher named Paul Feyerabend, who would later become one of the most famous philosophers of science of the 20th century, attended a conference in Bristol in 1957. The conference was the 9th symposium of the Colston Research Society, and the proceedings were published as Observation and Interpretation. Bohm was there, by that point, in exile from the United States, for 6 years, based briefly in Bristol, before his move to Birkbeck College. He presented his causal interpretation. Rosenfeld was in the front row, Feyerabend watched the exchange. He wrote about it later in his autobiography, Killing Time, in a passage that is perhaps the single most precise description of the sociology of the Bohm suppression ever written. Quote, "Confronted with the experiments, Rosenfeld and others occasionally acted almost as some of Galileo's opponents must have acted when confronted with the telescope." Unquote. Feyerabend went on to publish in 1960 in the British Journal for the Philosophy of Science a paper called Professor Bohm's Philosophy of Nature, in which he defended the causal interpretation against the Copenhagen orthodoxy. Feyerabend's later work on scientific pluralism, on the incommensurability of paradigms, on the social construction of scientific consensus, grew directly out of what he saw happen to Bohm in that Bristol conference room. The philosophy of science has been working out the implications of Bohm's suppression ever since. But these are philosophers and historians. They are not physicists. The professional consensus inside physics was and is that Bohm's theory is a technically correct but uninteresting construction, a curiosity for specialists, nothing a serious person builds a career on. This consensus did not emerge from scientific argument. It emerged from professional norms, from career incentives, from the social enforcement of acceptable questions, and from the specific private decisions of specific named men. And the man at the center of the story, the man whose theory was being ignored, was in 1952 not in a position to fight back. He was on a plane to Sao Paulo. He was about to learn what happens to an American physicist whose government has decided he is an embarrassment. The subpoena arrived at Palmer Physical Laboratory on the Princeton campus on April 21st, 1949. Bohm was 31 years old, an assistant professor in the third year of a 4-year contract, and had just begun to have some sense that the Copenhagen account of quantum mechanics might not be the whole story. He was also, though he did not yet know it, under active FBI surveillance as a former member of the Communist Party of the United States. The Bureau had, since 1943, been tapping the phone of a San Francisco party functionary named Steve Nelson. In those wiretap records, the names of the Berkeley Radiation Laboratory scientists appeared with some frequency: Bohm, Lomanitz, Weinberg, Friedman. The FBI had, by 1949, put together a picture of the Berkeley group as a cell of Soviet sympathizers who had been in close proximity to the Manhattan Project, and who might therefore have passed secrets to the USSR. The picture was mostly wrong. The wartime party meetings had been about civil rights and campus politics, not about nuclear weapons. There is no evidence in any of the material that has since been declassified that Bohm ever knew anything classified, let alone passed anything to anyone. He had not even been allowed to read his own thesis. But the HUAC subpoena was not a tool of truth-finding. The HUAC subpoena was a tool of public theater, and the theater had already been cast. Bohm testified before the House Un-American Activities Committee twice, on May 25th and June 10th of 1949. The transcripts are a matter of public record. He was asked about his time at Berkeley. He was asked whether he had been a member of the Communist Party. He was asked to identify other members, and he invoked the Fifth Amendment to the Constitution of the United States, which protects a witness from being compelled to give testimony that might incriminate him. He did this consistently. He did not name names. Joseph Weinberg, whom the committee was especially interested in, had been his friend at Berkeley. Giovanni Rossi Lomanitz had been his friend at Berkeley. David Hawkins had been his friend at Berkeley. Bohm knew them all, and Bohm refused to say so. And every refusal was a small, deliberate act of courage, the committee noted with growing irritation. There was an irony. Oppenheimer had already testified. Oppenheimer, on June 7th of 1949, just before Bohm's second appearance, had sat before the committee and named people. He had named Bohm. He had named Lohmanitz. He had named Bernard Peters. He had told a security officer, Pierre de Silva, that he considered Bohm and Peters to be, quote, truly dangerous, unquote. That phrase, truly dangerous, was used by a man who had been Bohm's mentor, about a physicist who had never held a security clearance and had never been granted access to any classified information. Oppenheimer was cooperating to save himself. The cooperation did not, in the end, save him. In 1954, the Atomic Energy Commission would revoke his security clearance after a humiliating closed hearing in which the same cooperation was used against him. The Cold War security apparatus consumes its informants. The pattern is consistent across decades. Princeton University did not take Bohm's legal difficulties in stride. His contract ran through June 30th of 1951. In November of 1950, the Princeton Physics Department voted to recommend his reappointment for another term. The recommendation was overruled by the university administration, specifically by President Harold W. Dodds, who had decided that Bohm's public association with communism was an embarrassment to the university and that his contract would not be renewed, acquittal or no acquittal. Dodds wrote in an internal document, quote, I feel that the university must recognize that Professor Bohm has not indicated that he possesses those qualities of personality and judgment which should be expected of a member of its faculty, unquote. In December of 1950, Bohm was suspended. He was forbidden to set foot on the Princeton campus, not just the physics building, not just his office, the entire campus, including the library. An assistant professor of physics was barred from the stacks of the Firestone Library in December of his fourth year on the faculty because the university was worried about optics. He was indicted for contempt of Congress on December 4th of 1950 for having refused to name his Berkeley colleagues. He posted bail. He was tried in late May of 1951. He was acquitted. The judge, looking at the record, concluded that the Fifth Amendment protections Bohm had invoked were legally valid and that no contempt had occurred. Bohm was a free man, cleared of all charges, with his legal record intact. His Princeton contract ended, as scheduled, on June 30th of 1951. He was unemployed. No American university would hire him. He wrote letters to physics departments across the country. He received polite refusals, and in most cases, no answer at all. The blacklist was not a formal document. It was an informal professional consensus, enforced through the shared understanding of department chairmen who knew, without anyone ever writing it down, that hiring David Bohm in 1951 was a career risk. Einstein tried to help. This is one of the most affecting parts of the story, and also one of the most painful, because of how little it accomplished. Einstein had known Bohm since his arrival in Princeton in 1947. He had read his textbook. He had had the long conversation that would, a year later, catalyze the 1952 papers. Einstein was 72 years old, in declining health, and still the most famous scientist in the world. He wrote letters on Bohm's behalf. He lobbied colleagues, and most significantly, he wanted to hire Bohm as his own research assistant at the Institute for Advanced Study. Einstein at the Institute, Bohm working directly with him, producing the theory that would vindicate Einstein's 50-year opposition to Copenhagen. It would have been one of the great scientific partnerships of the century. It did not happen. It did not happen because Robert Oppenheimer was the director of the Institute, and Oppenheimer blocked it. This is documented in David Cassidy's 1995 biography of Oppenheimer, J. Robert Oppenheimer and the American Century, on page 282. Cassidy writes that Einstein wanted Bohm to serve as his assistant, and that Oppenheimer, quote, opposed the idea and advised his former student to leave the country, unquote. Read that sentence again. Oppenheimer opposed the idea of his own former student working for Einstein and advised his former student to leave the country. The man who had certified Bohm's doctoral thesis sight unseen during the war was, 7 years later, using his institutional power to ensure that Bohm could not remain in America even as a research assistant to an eccentric old man in his final years. Oppenheimer did write a formal letter of recommendation for Bohm's move to Sao Paulo. The letter was polite. The letter was effective. The letter functioned exactly as an eviction notice. Einstein appears to have accepted the situation with resignation. He knew, better than anyone, what institutional pressure could do to a career. He had left Germany in 1933, for reasons not entirely unlike the reasons Bohm was now leaving America in 1951. The parallels are uncomfortable. Einstein wrote in private correspondence during this period about what it meant to watch an American university behave the way he had watched German universities behave 20 years earlier. The phrase he used in a letter auctioned in Jerusalem in June of 2017 was that he found the situation, quote, shameful, unquote. There were 5 Einstein-Bohm letters in that auction, covering McCarthyism, God, and Israel. At least one of them sold for $84,000. Jaime Tiomno, a Brazilian physicist who had done his doctoral work at Princeton under Eugene Wigner, heard about Bohm's situation. He was in the process of building a theoretical physics program at the University of Sao Paulo. He contacted Bohm. He offered a full professorship. He arranged for Bohm to be invited, for the visa paperwork to be processed, for a salary and an office to be provided. Abraão de Moraes, the professor of theoretical physics at Sao Paulo, supported the appointment. Recommendation letters came from Einstein and, as noted, from Oppenheimer. Bohm accepted. He arrived in Sao Paulo on October 10th of 1951. He had, by that point, already submitted the 2 papers that would appear in Physical Review 3 months later. He did not know he was about to lose his passport. The events of late October 1951 are documented in the Bohm archive at Birkbeck College in London. Reference numbers A122 through 129. Less than a month after his arrival, Bohm received a notification from the United States Consulate in Sao Paulo. He was requested to come in for a routine matter relating to his travel documents. He went in. He was informed that his passport was being confiscated at the direction of the State Department, and that it would only be returned to him if he agreed to board a flight directly back to the United States. He could fly home, or he could remain in Brazil as a stateless person. Those were the options. The State Department had reviewed his status and decided that this particular American abroad was not going to remain an American abroad. The passport was the weapon. Without a passport, Bohm could not attend international physics conferences. He could not travel to Europe to meet with Einstein, with Pauli, with any of the people who might have engaged with his theory in person. He could not return to the United States except as a man coming home to answer further questions. He was sealed in Brazil, and the papers that were about to appear in Physical Review in January, were about to be published by an author who could not travel to defend them. The initial reception in the United States physics community, hostile as it was, took place in absolute Bohm's absence. He could not stand up at the APS meeting and answer objections. He could not be in the room when Oppenheimer convened his meeting to discuss the papers. He could not do the ordinary professional work of promoting a new theory. The State Department had, by confiscating a small booklet with a photograph in it, accomplished something the physics establishment might have struggled to accomplish on its own. They had made him voiceless inside his own discipline. He wrote about this period in letters that have survived. The letters are, by turns, dignified and devastating. To a correspondent on October 6th of 1953, he wrote, quote, "I am afraid that Brazil and I can never agree," unquote. To another, around the same time, quote, "I have to apologize for not answering your last letter, but I've been tired and depressed," unquote. He found the climate oppressive. He could not speak Portuguese, though he learned enough to teach theoretical physics in the local language by the end of 1953. He was isolated. Jean-Pierre Vigier, the French physicist who had worked with de Broglie, came from Paris for 3 months to collaborate. Ralph Schiller came from the United States and stayed for 2 years as Bohm's assistant. Mario Bunge came from Argentina for a year. These were generous acts of solidarity by colleagues who understood that Bohm was a prisoner in his circumstances. But they were the exceptions. Most of the physics community internationally did what institutional self-interest told them to do, which was to not get involved, to keep their distance, to let the situation resolve itself on terms set by the United States government. The situation resolved itself in a way that made it worse. In 1954, Bohm applied for Brazilian citizenship. This required him to renounce his American citizenship. The United States had, by refusing to return his passport, constructively forced this choice on him. If he wanted to be a citizen of any country, he needed to be a citizen of Brazil, because he was not allowed to be a citizen of the United States anywhere other than inside it. He renounced. He became a Brazilian national. He did not recover his American citizenship until 1986, 35 years later, after filing a federal lawsuit against the State Department. By the time the case was decided, he was 68 years old. He had been in exile for a working life. The Cold War was almost over. Nobody cared anymore about whether David Bohm was an American. He had been punished for a set of political beliefs he had held, briefly, in his 20s. And by the time the punishment was rescinded, most of the punishers were dead, and most of his career was behind him. Einstein had, as a precaution, written a letter to President Getúlio Vargas of Brazil in May of 1952 to be held in reserve in case Bohm faced political trouble from the Brazilian government. The letter was never needed. The Brazilian authorities left Bohm alone. The persecutors were at home. They sent their subpoenas from Washington and their directives from Foggy Bottom, and they watched with the patience of men who knew they had all the time in the world. As the theorist whose work they could not engage with settled into a quiet provincial exile that would eat up a decade of his most productive years, Bohm did not stop working. This is the part of the story that, for me, is the hardest to come to terms with. You would expect, under these conditions, that a man would break. And Bohm did, in his own way, break. He was depressed for most of the 1950s. He was hospitalized for depression multiple times over the course of his life. He had, by the end, received 14 bilateral electroconvulsive treatments at the Maudsley Hospital in London in the summer of 1991. The psychiatric history is documented in the Pete biography and is substantial. He was not a serene sage. He was a man operating at the edge of what a mind can bear, in exile, under institutional erasure, with his own discipline having voted to pretend he did not exist. And he kept writing. In 1953, he and Jean-Pierre Vigier published a paper in Physical Review, extending the pilot wave picture to incorporate stochastic fluctuations, a paper that anticipated by decades the work Anthony Valentini would later do on quantum non-equilibrium. In 1957, he published a book called Causality and Chance in Modern Physics, a philosophical defense of his interpretation of quantum mechanics that is still in print. In 1959, by which point he had moved from Brazil to Israel to Bristol, he and his student Yakir Aharonov published in Physical Review the paper that discovered the Aharonov-Bohm effect. I want to dwell on the Aharonov-Bohm paper for a moment because it deserves its own small digression. The paper showed that the electromagnetic vector potential, which the standard view treated as a mathematical convenience with no independent physical reality, in fact has direct observable consequences for quantum particles, even in regions of space where the electromagnetic field is zero. You can send an electron through a region that has no electric or magnetic field present, and if the vector potential in that region is non-zero, the electron's wave function picks up a phase shift that can be measured in subsequent interference experiments. The paper was published in Physical Review, volume 115, pages 485 to 491, in August of 1959. Richard Feynman, reading it, reportedly sent Bohm a telegram that read, quote, "How beautiful, how come I never thought about it myself?" Unquote. Feynman, whatever else he was, had excellent taste. The effect was experimentally confirmed by R.G. Chambers in 1960, and then definitively by Akira Tanomura and collaborators in 1986. The Aharonov-Bohm effect is today considered one of the foundational results of quantum mechanics. It appears in every graduate textbook. It is used in the design of quantum devices. Its author, by the time it was published, was sitting in a Bristol office that had been arranged for him because no American institution would touch him. The Aharonov-Bohm effect is not strictly a vindication of pilot wave theory. It does not require the Bohm interpretation, but it has a particular philosophical flavor that is hard to ignore. It shows that the wave function is sensitive to features of the physical world, the vector potential, that cannot be reduced to the local field values the classical picture treated as fundamental. It shows, in other words, that the wave function has a kind of reality that extends into regions of space where standard intuitions would say nothing is happening. This is exactly the kind of reality Bohm's papers had attributed to the wave function in 1952. The theory that Oppenheimer had told the Institute to ignore was, through the Aharonov-Bohm effect, quietly shaping the textbooks anyway. The orthodoxy had to cite Bohm's name to teach one of the most important results in modern quantum mechanics. The orthodoxy hated that. The orthodoxy did it anyway, because the physics was too beautiful to leave out. By 1961, Bohm had moved for the last time. He took a professorship at Birkbeck College in the University of London, where he would remain for the rest of his career. He had married in 1956 in Israel, Sarah Wolfson, who would be his partner for the next 36 years. He had students who loved him. Basil Hiley, whom he hired at Birkbeck in 1961, would become his closest collaborator for the remaining 31 years of his life. He was, by any external measure, no longer in exile. He had a post, he had tenure, he had an office, but the foundational work on quantum mechanics had stopped being considered important by the mainstream. In the United States especially, where the action in physics was, the intellectual climate Oppenheimer had helped create, in which foundational questions were treated as philosophical self-indulgence and practical calculation was the only legitimate activity, had solidified into a full-blown culture. The culture had a slogan. The slogan was, "Shut up and calculate." And the consequences of that slogan were that Bohm's theory, however beautifully formulated, however empirically adequate, would continue to be, in the phrase Sheldon Goldstein of Rutgers University used in a 2016 interview, quote, "the kiss of death for a physics career," unquote. There was a time, Goldstein said, when you could not even talk about it because it was heretical. It probably still is. I want you to hold that phrase in mind. The kiss of death, the language of betrayal. The physics community that had just watched one of its most gifted members be stripped of his citizenship for thought crimes had adopted, as its ongoing professional norm, the position that engaging with his work would end your career. There is a line in John Bell's writing about this period where he describes the situation with extraordinary precision. I will share it with you, but I want you to let the previous sentence sit for a second first, because what I am about to read you is a description of the discipline that produced everything you know about the physical world, and the description is not flattering. John Stuart Bell was born on July 28, 1928, in Belfast, Northern Ireland. His father, John Bell Sr., was a horse dealer. His mother, Annie, sewed his academic gown, when he eventually needed one, from blackout curtains left over from the war. The Bell family had no scientific background. They were working-class Protestants in a city defined by religious and class division, and they did not move in the circles where academic futures were planned. John Bell went to the Belfast Technical High School and then to Queen's University Belfast, where he earned 2 separate Bachelor of Science degrees, one in experimental physics in 1948 and a second in mathematical physics in 1949. He was, in the language his colleagues would later use, an outsider twice over. He was an outsider to the English establishment because he was Irish. He was an outsider to the physics establishment because he had come up through provincial institutions without the American or continental pedigree that mattered in the field. And he was an outsider to the Copenhagen orthodoxy because he had taken as a student a look at the standard quantum mechanical textbook argument and concluded that something about it did not add up. In 1952, while working at the United Kingdom Atomic Energy Research Establishment at Harwell, John Bell was 24 years old and had encountered Bohm's 2 papers in Physical Review within days of their publication. He read them, he understood them. He recognized immediately that they did something his teachers had told him was impossible. Many years later, in a paper titled On the Impossible Pilot Wave, published in Foundations of Physics in 1982, Bell wrote down what reading those papers had been like. The passage is worth quoting in full. because it is the single most important personal testimony in the entire history of quantum foundations. Quote, "But in 1952, I saw the impossible done. It was in papers by David Bohm. Bohm showed explicitly how parameters could indeed be introduced into non-relativistic wave mechanics, with the help of which the indeterministic description could be transformed into a deterministic one. More importantly, in my opinion, the subjectivity of the orthodox version, the necessary reference to the observer, could be eliminated." Unquote. I want you to hear the texture of that passage. Bell is 24 years old in 1952. He has just come out of university. He has been taught, as everyone in his generation was taught, that hidden variables are mathematically impossible. Von Neumann said so. Born said so. His professors said so. And then he reads these papers and sees that the impossibility was never an impossibility, that it was a rhetorical settlement, that the emperor had no clothes. He saw it at 24. He did not have the standing to publish a demolition of von Neumann in 1952. He had not even begun his doctoral work. But he knew from that year forward that the entire field was sitting on top of a collective misreading. It would take him 14 years to write it down. Bell's paper on the problem of hidden variables in quantum mechanics was submitted to reviews of modern physics around 1963 and appeared in print on July 1st of 1966 in volume 38, pages 447 to 452. The paper sat in an editorial drawer at the journal for over a year before it was processed. This is a fact Hermann confirms in his writings about the episode. One of the most important papers in the history of 20th century foundations of physics was, for a period longer than most papers wait for peer review, simply forgotten on an editor's desk. There is an argument to be made that this neglect was itself a symptom of the same professional dynamic that had suppressed Bohm. An interpretive paper by an unknown on a topic everyone had agreed not to discuss did not rise to urgent attention. When it finally appeared, the paper did to von Neumann's theorem exactly what Greta Hermann had done in 1935, 31 years earlier, without knowing that Hermann had done it. Bell identified the unphysical additivity assumption. He showed it was not required of any serious hidden variable theory. He concluded that von Neumann's proof did not prove what von Neumann had claimed it proved. He did this with the characteristic Bell clarity, which is a clarity achieved through ruthless elimination of everything that is not essential. And then, at the end of the paper, he wrote a sentence that would change physics. He wrote, quote, "It would therefore be interesting, perhaps, to pursue some further impossibility proofs, replacing the arbitrary axioms objected to above by some condition of locality." Unquote. Translate that out of Bell's understated academic prose. What he is saying is, the existing impossibility proof is broken, but maybe there is a different impossibility we can prove, based not on arbitrary mathematical assumptions, but on a physical condition, the condition that distant events cannot instantaneously affect each other. If we assume locality, the condition that classical physics always took for granted, can we prove that no hidden variable theory can reproduce the predictions of quantum mechanics? That question, posed at the end of the 1966 paper, was what Bell had been working on in parallel for the previous 2 years. He had, in fact, already found the answer. He had published it in 1964. The paper was titled On the Einstein-Podolsky-Rosen Paradox. It appeared in a short-lived journal called Physics, in Volume 1, issue 3, pages 195 to 200. In November of that year, the journal had a circulation of roughly 1,000 readers and folded shortly thereafter. The paper proved what is now called Bell's theorem. The theorem says this: if you assume that the world is local, that no influence can travel faster than light, and that the particles in an experiment have definite properties prior to being measured, then certain statistical relationships must hold between measurement outcomes on pairs of particles. These relationships are called Bell inequalities. Quantum mechanics predicts that the inequalities are violated. The experimental observation, which Clauser and Friedman first reported in 1972, and which was progressively refined through Alain Aspect in 1982, and the loophole-free experiments of 2015, is that the inequalities are in fact violated by margins far beyond any statistical noise, exactly as quantum mechanics predicts. Therefore, the world is either not local, or the particles do not have definite properties prior to measurement, or both. Every local hidden variable theory is experimentally ruled out. Bell's theorem is, today, considered one of the most important results in 20th century physics. The experimental work that confirmed it won the 2022 Nobel Prize in Physics for John Clauser, Alain Aspect, and Anton Zeilinger. Bell himself did not live to see the prize. He died in Geneva on October 1st, 1990, of a cerebral hemorrhage. At the age of 62, he had reportedly been nominated for the Nobel Prize that same year. The nomination did not convert to a prize in time. The Nobel is not awarded posthumously. Bell missed it by months. Here is what I want you to understand about the relationship between Bell's theorem and Bohm's theory, because this is the connection that almost nobody explains correctly in the popular literature. Bell's theorem did not refute Bohm. Bell's theorem vindicated Bohm. Bohm's theory is explicitly non-local. The quantum potential connects distant particles instantaneously. The guiding equation for any given particle depends on the positions of all other particles across arbitrary distances through the global wave function. This is not a bug in Bohm's theory. This is a feature Bohm built into the theory from the beginning, honestly and explicitly. Bell's theorem proved in 1964 that any hidden variable theory that reproduces the predictions of quantum mechanics must have exactly this feature. Non-locality is not optional, it is required. So when you ask, in 1990 or 2000 or 2025, why did the physics community reject Bohm's theory? The answer cannot be that the theory had objectionable non-locality. Any theory that gets quantum mechanics right has that same non-locality. The only difference is that Bohm's theory is honest about it, and standard quantum mechanics hides it behind language about collapse and complementarity. The Copenhagen interpretation is just as non-local as pilot wave theory. Copenhagen simply does not describe the non-locality in explicit mathematical form, so its defenders can pretend it is not there. Bohm's theory refuses that pretense. That is the real sin. That is what Rosenfeld meant when he called it obscurantism, and Pauli called it bad taste. They were not objecting to the physics. They were objecting to the physics being made visible. Bell knew this. Bell said it in print in his characteristically calm Irish inflected prose in the same 1982 paper. Quote, "Why is the pilot wave picture ignored in textbooks? Should it not be taught? Not as the only way, but as an antidote to the prevailing complacency, to show us that vagueness, subjectivity, and indeterminism are not forced on us by experimental facts, but by deliberate theoretical choice." Unquote. Deliberate theoretical choice. That phrase is the quiet, devastating verdict on 70 years of intellectual history. The vagueness and subjectivity of standard quantum mechanics are not dictated by nature. They are chosen by the people who write the textbooks. The experimental facts allow other choices. The other choices have been suppressed. Bell is naming explicitly what the discipline has been doing, and he is naming it to the discipline in its own journals, under his own name, and very few physicists have ever been comfortable engaging with what he said. There is one more Bell passage I need to share with you. It is from a paper published in 1984, reprinted in his collected essays, Speakable and Unspeakable in Quantum Mechanics. Here is the passage. Quote, "Bohm's 1952 papers on quantum mechanics were for me a revelation. The elimination of indeterminism was very striking, but more important, it seemed to me, was the elimination of any need for a vague division of the world into system on the one hand and apparatus or observer on the other. I have always felt since that people who have not grasped the ideas of those papers, and unfortunately they remain the majority, are handicapped in any discussion of the meaning of quantum mechanics." Unquote. Handicapped in any discussion of the meaning of quantum mechanics. The physicist who won, or should have won, the Nobel Prize for the most important theorem in quantum foundations, wrote in his collected essays that the majority of his colleagues were handicapped in the relevant conversations because they had not read the two papers the discipline had agreed to pretend did not exist. Let that sentence sit. The majority of professional physicists, according to John Bell, could not have an informed discussion about the foundations of their own field because they had not done the reading, because the reading had been stigmatized. Sheldon Goldstein, a mathematical physicist at Rutgers who spent a significant portion of his career working on the mathematical rigorization of Bohmian mechanics, put it this way in a 2016 interview, quote, "About half of the papers in Bell's collected works on the foundations of quantum mechanics deal with Bohmian mechanics." Unquote. Half. The papers of the man who proved the most important theorem in the field are half about the theory the field agreed to ignore. This is what institutional capture looks like when it encounters actual rigor. The rigor goes on. The institution remains captured. The two operate in parallel, and the discipline tells the public about the institution and not about the rigor. The experimental vindication of Bell's theorem, which is the experimental vindication of Bohm's nonlocality, unfolded over 50 years. The first serious attempt at testing the Bell inequalities was by John Clauser and Stuart Friedman at the University of California at Berkeley in a paper published in Physical Review Letters in 1972. Clauser was, at that point, a young postdoctoral researcher. His faculty at Columbia had told him, when he proposed this line of research, that testing quantum physics was going to destroy his career. He did the work anyway, at Berkeley, in relative isolation. In a 2003 essay, he would later describe the professional climate in strikingly precise terms. Quote, "My faculty at Columbia told me that testing quantum physics was going to destroy my career. While I was performing the 1972 Friedman-Clauser experiment at UC Berkeley, Caltech's Richard Feynman was highly offended by my impertinent effort and told me that it was tantamount to professing a disbelief in quantum physics." Unquote. Clauser describes a, quote, "very powerful stigma," unquote, against anyone who questioned foundations. Any physicist who did, in his words, was immediately branded as a quack. Clauser and Friedman found the inequality violated to about 6 standard deviations. Quantum mechanics won. Local hidden variable theories lost. The result was published. The result was confirmed by Alain Aspect in Paris in 1982 at higher precision, with the additional refinement that the measurement settings were changed during the flight time of the photons, closing a potential loophole. The result was confirmed again at higher and higher levels of rigor by a succession of experiments through the 1990s and 2000s. In 2015, 3 independent groups in Delft, in Vienna, and at the NIST laboratory in Colorado closed the last remaining loopholes simultaneously. The result held. The world is non-local. The 2022 Nobel Prize in Physics, awarded to Clauser, Aspect, and Zeilinger, was in effect a Nobel Prize for proving, experimentally, something that Bohm's 1952 theory had predicted as a direct mathematical consequence of its fundamental equations. Bohm did not live to see the Nobel. He had died 30 years earlier. Bell did not live to see the Nobel. He had died 32 years earlier. The 2 physicists whose work was vindicated by the experimental program that culminated in the 2002 prize were both safely dead before the prize was awarded. This is how the pattern keeps working. The vindication arrives. The vindication arrives just late enough. I want you to take a moment with me here, because we have just walked through a very long sequence of events, and I want to make sure it has accumulated properly. In 1952, David Bohm published a theory that said quantum mechanics is underwritten by a deterministic dynamics with definite particle positions and an explicitly non-local guiding wave. The physics establishment said he was wrong, or more precisely, said he was an embarrassment. In 1966, John Bell published a paper showing that the central mathematical argument against Bohm's theory was defective. In 1964, Bell had already published the theorem that proved non-locality is not optional, that any hidden variable theory must be non-local, that Bohm's explicit non-locality was a feature of reality rather than a defect of his theory. Between 1972 and 2015, experimental physics confirmed to more than 30 standard deviations that non-locality is in fact a feature of reality. In 2022, this experimental program received the highest honor in the field. And in July of 2005, a survey of over 1,000 professional physicists found that 7% of them identified pilot wave as their preferred interpretation, while 76% declined to commit to any interpretation at all. The pattern across 73 years is this: Bohm was right. The field knew he was right, or they would not have had to work so hard to pretend otherwise. The field punished him for being right because the implications of his rightness were too heavy to carry professionally. The field then slowly, over decades, came to accept the specific experimental consequences of his theory, while continuing to avoid the theory itself, because the theory is too honest about what reality has to be like for those consequences to hold. The field today teaches students a patchwork of avoidances. It teaches them Bell's theorem without teaching them that Bell's theorem exists because Bell read Bohm. It teaches them quantum computing applications of entanglement without teaching them that entanglement is non-local in a way that is only made mathematically explicit by the interpretation they have been told not to take seriously. It teaches them that we have a successful theory of nature while refusing to say what the theory is a theory of. Bell himself had the cleanest diagnosis of this situation. I am going to read you one more of his sentences, and then we are going to move to the last section of this story. This is from his 1981 paper Bertelsmann's Socks and the Nature of Reality. Quote, making a virtue of necessity and influenced by positivistic and instrumentalist philosophies, many came to hold not only that it is difficult to find a coherent picture, but that it is wrong to look for one if not actually immoral, and certainly unprofessional. Unquote. Immoral. Unprofessional. You should not merely be wrong to look for a coherent picture of reality. Bell is saying, you should be ashamed. That is the professional norm the discipline has trained itself into. Asking what physics is actually describing is, in the working culture of 20th century theoretical physics, a moral failure. The man who wrote that sentence won, or should have won, every prize the field gives. He died in a hospital in Geneva. His collected essays, which are in print and which you can order from Cambridge University Press for about £40, are read by a small minority of the people who actually work on quantum mechanics. The field has arranged itself in such a way that he is revered and ignored simultaneously. He is cited and shelved in the same motion. And I want to say, as honestly as I can at this point in the argument, that this pattern is what is happening in every physics department I know anything about. Right now, as we speak, the current generation of graduate students is being trained into the same habits of avoidance that trained their teachers. There is no villain in this. There is no conspiracy. There is only a discipline that has found a stable equilibrium in which the hardest questions are the ones nobody is professionally incentivized to ask. And the answer, in the form of a set of papers that solve the measurement problem and tell you what the wave function is and give you a deterministic dynamics for the whole observable world, has been sitting on the library shelf since January of 1952. And the price of the incuriosity has been, among other things, the life of one brilliant man. Before we come to the end of Bohm's life, I want you to see the experimental present. I want you to understand that this is not a closed chapter. The theory is alive. The experiments are ongoing. The vindications, when they come now. In 2011, a team led by Ephraim Steinberg at the University of Toronto published a paper in the journal Science in volume 332, pages 1170 to 1173. The title of the paper was Observing the Average Trajectories of Single Photons in a Two-Slit Interferometer. Let me tell you what they did. They built a double-slit apparatus for individual photons, of the kind we have been discussing throughout this video. But they added a refinement, using a technique called weak measurement, which had been developed theoretically by Yakir Aharonov, the same Aharonov who had been Bohm's student at Bristol in the 1950s. The Toronto group was able to extract information about the momentum of each photon at intermediate points along its path, without disturbing the photon enough to destroy the interference pattern. This is a subtle technique. It does not violate the uncertainty principle. It works by measuring the momentum so gently that the information obtained about any single photon is mostly noise, but when you average over many photons, a coherent picture emerges. And the picture that emerged was the picture of the photons' average trajectories through the apparatus. You can plot them. They form smooth, non-crossing curves that start at one of the two slits, bend through the interference region, and arrive at specific regions of the detection screen. They look exactly like the Bohmian trajectories Dewdney, Philippides, and Hiley had computed 32 years earlier. The paper did not quite have the nerve to draw the explicit conclusion. The authors, working in a field that still stigmatizes the Bohm interpretation, were careful to describe the results as weak measurement reconstructions of average trajectories, rather than as confirmation of the Bohmian picture. But the mathematics is unambiguous. Howard Wiseman had shown in a 2007 paper in New Journal of Physics that a weak measurement of velocity post-selected on a subsequent position measurement yields exactly the Bohmian velocity. The Toronto experiment was, in all but name, a direct observation of Bohmian trajectories. It was in the journal Science. It was cited in hundreds of subsequent papers. It was ignored by the people writing textbooks. In 2016, a group at the University of Toronto extended the work to entangled photons. The paper, published in Science Advances, showed that the weakly measured trajectories of entangled photon pairs exhibit explicitly non-local behavior. When you change the measurement being performed on one member of an entangled pair, the reconstructed trajectory of the other member changes instantaneously at arbitrary distances. You can see the non-locality. You can plot it. The plot shows what Bohm's 1952 papers predicted the plot would show. 71 years of experimental physics. One consistent verdict. Bohm was right about the structure of reality. There is a separate line of experimental work I should mention briefly because it has been the subject of some popular science coverage, and I want you to have an accurate picture of what it does and does not show. In 2005 and 2006, Yves Couder and Emmanuel Fort at the Université Paris-Diderot discovered a striking macroscopic analog of pilot wave dynamics. If you take a shallow bath of silicone oil and vibrate it vertically at just below the threshold where the surface spontaneously breaks into waves, and you drop a small droplet of the same oil onto the surface, the droplet will bounce repeatedly on the surface without coalescing. Each bounce generates a small surface wave, which spreads outward and interacts with the droplet on subsequent bounces. And the result is a system in which the droplet propels itself across the bath, guided by its own wave. The behavior is in many respects a macroscopic mechanical analog of the Bohmian pilot wave. The droplet has a definite position. The wave guides it. The droplet can even exhibit analogues of single-slit diffraction, quantized orbits around centers of attraction, and tunneling through barriers. John Bush at MIT has led the theoretical analysis of these systems since about 2010. The analog is provocative. It is also limited. The droplet system cannot reproduce entanglement. It cannot reproduce Bell inequality violations because those require non-local connections that a purely mechanical system on a water surface cannot produce. And in 2015, 3 independent groups showed that earlier claims of single photon-like double-slit behavior in droplets were not as clean as Couder and Fort had initially suggested. I mention all of this because I want to be honest with you. The droplet experiments do not prove pilot wave theory. They provide a compelling visual and physical intuition for what a deterministic pilot wave system can and cannot do. They are a pedagogical tool. They are not an empirical confirmation. The empirical confirmation of the pilot wave structure of reality, if we have one, comes from the Bell inequality experiments and from the weak measurement reconstructions, not from the oil droplets. There is another line of current research I find more consequential, and I want to describe it briefly. Anthony Valentini, now at Clemson University, is one of the most serious contemporary defenders of the pilot wave interpretation. His doctoral work Completed at the International School for Advanced Studies in Trieste in 1992, under Denis Sayama, extended Bohm's framework in a direction Bohm himself had suggested, but not pursued rigorously. Valentini's central idea is that the equilibrium condition under which Bohm's theory reproduces standard quantum mechanics is exactly that, an equilibrium analogous to thermal equilibrium in classical statistical mechanics. The Bohm rule, the rule that says the probability of finding a particle in a given region is given by the square of the wave function amplitude, is in Valentini's picture not a fundamental postulate of nature. It is a stable attractor. The universe relaxes to it over time, the way a hot object relaxes to the temperature of its surroundings. And just as classical systems can be in non-equilibrium states, at least locally and temporarily, Valentini argues that the universe might contain, or might once have contained, regions of quantum non-equilibrium in which the Bohm rule does not hold. The implications of this are genuinely strange. If quantum non-equilibrium exists, then in the relevant region or epoch, the uncertainty principle is not fundamental. Signaling faster than light becomes, at least in principle, possible. Computation beyond the capabilities of conventional quantum computing becomes, at least in principle, possible. Valentini has argued that the earliest moments of cosmic inflation, when the universe was expanding exponentially and no local process had had time to bring any region into equilibrium with any other, might have generated measurable deviations from the Bohm rule, deviations that could still be present in the cosmic microwave background, as small statistical anomalies in the distribution of temperature fluctuations. These deviations, if they exist, would be fossils of a non-equilibrium period in the very early universe, and they would be, if observed, the first direct empirical signature of a physics beyond standard quantum mechanics. Valentini has written, in a passage I find hard to shake, quote, "Immense physical resources for non-local communication, espionage, and exponentially fast computation are hidden from us by quantum noise," unquote. The noise, he is saying, may be masking a universe that is in principle much more manipulable than the one we have been led to expect. I want to say, I am uncertain whether Valentini is right about the specific observational signatures. The cosmic microwave background data is consistent with standard inflation and has not shown a clear sign of quantum non-equilibrium anomalies at the precision currently available. But his larger framework, in which the Bohm rule is a statistical equilibrium rather than a fundamental postulate, is a direct extension of Bohm's 1952 ontology. It is the kind of research program that Bohm's theory makes natural and that standard Copenhagen quantum mechanics cannot support, because standard Copenhagen has no sense in which the Bohm rule could be derived rather than assumed. The tree that was cut down in 1952 has, it turns out, been putting out branches the entire time. They just do their growing in the quieter journals. All of which brings us back to that 2025 survey. 1,100 physicists, 36% Copenhagen, 15% many worlds, 7% pilot wave, 24% confident in anything. The survey was published in Nature on July 30th, 2005, and has been cited by basically every serious philosopher of science in the subsequent months, because it is, at last, the quantitative confirmation of something Bell had described in prose 40 years earlier. The discipline does not know what its own theory means. The discipline has not made a collective decision about the foundations. The discipline is, to put it as directly as I can, dispersed across a field of disagreement that 70 years of avoided conversation have prevented from ever converging on an answer. Renato Renner, a physicist at ETH Zurich, told the Science Press when the survey was published, quote, "The implication is that many quantum researchers simply use quantum theory without engaging deeply with what it means. The shut up and calculate approach," unquote. Robert Speckens, of the Perimeter Institute, was less diplomatic. He said that many physicists are, quote, "just drinking the Kool-Aid of the Copenhagen philosophy without examining it," unquote. That is 2025. That is the current state of the conversation. 9 decades after von Neumann's proof, 7 decades after Bohm's papers, 6 decades after Bell's theorem, 5 decades after the Clauser-Friedman experiment, 3 years after the Nobel Prize for Bell inequality tests, and the professional physics community is still dispersed across a field of interpretations, none of which the majority of its members actually believes. The question of what quantum mechanics is a theory of has not been answered. It has not even been seriously joined. The field has a technology that works, and the field uses the technology, and the field has made a separate informal agreement that the meaning of the technology is a topic for the philosophy department. You were never told this. I was never told this. I went through a standard physics education, and I never encountered a clear presentation of the fact that the most sophisticated and rigorously defended mathematical interpretation of quantum mechanics is one my textbooks did not bother to discuss, and my professors would not have been willing to defend in a seminar. I encountered Bohm's name, if at all, as a footnote. The footnote said something non-committal. The footnote did not say, "This man solved the measurement problem and was destroyed for doing it." The footnote did not say, "The physics community's decision to ignore his work is a case study in how professional norms prevent the discipline from converging on the truth." The footnote said, "Bohm also proposed a deterministic interpretation." And then the footnote ended, and the paragraph moved on, and the chapter moved on, and you never learned the thing you needed to learn about the theory that describes the particles in your body. I want to zoom out for a second, because I think this matters. The pattern I have been describing in this video, the pattern where a correct idea is suppressed by institutional inertia, and the suppression is enforced through career incentives, and the truth arrives on a schedule set by how long the careers of the suppressors happen to be, is not a pattern that is confined to quantum mechanics. It is the default mode of how institutional knowledge systems process uncomfortable truths. Plate tectonics waited 50 years between Alfred Wegener's original proposal in 1912 and the mid-60s consensus that finally accepted it. The Helicobacter pylori explanation for stomach ulcers waited decades after Barry Marshall's demonstration. Continental drift, dark energy, prion diseases, every one of them followed a similar arc. An outsider gets the answer. The institution rejects the answer for reasons that have nothing to do with the answer being wrong. The institution waits for the outsider to die, or to retire, or to become so marginalized that accepting the answer is no longer threatening to anyone's authority. The institution then quietly incorporates the answer, retroactively describes itself as having been on the right side all along, and prepares to repeat the process with whatever the next uncomfortable truth happens to be. This is happening in other fields right now. It is happening in biology, in medicine, in economics, in climate science, in artificial intelligence research. There are, in every one of those fields, correct answers to important questions that are currently being suppressed, not by malicious conspiracy, but by the same mechanism that suppressed Bohm: career incentives, professional norms, textbook inertia, the unspoken understanding among the senior people who control the flow of grants and the composition of editorial boards that certain questions are not to be asked, because asking them would destabilize too many existing positions. You are living right now inside the set of those suppressions. Across every topic you care about, some of the suppressions will be corrected in your lifetime. Some of them will not. For some of them, the outsider who has the answer has already done the work, and the work has been published, and the work is not being read, and you will finish your life without anyone telling you about it. The story of David Bohm is not an edge case. It is the case. It is what happens, and what is happening right now across the fields you personally rely on for information about the world you live in. The only unusual feature of Bohm's case is that it involved a field rigorous enough that the suppression can, in retrospect, be documented with forensic precision. In softer disciplines, the suppression is harder to see because the criteria for correctness are fuzzier. In physics, the criteria are sharp enough that the historical record is unambiguous. He was right. They ignored him. Here is what that looked like. And now, with all of that context, we can come to the end of Bohm's life, which is, I think, the hardest part of the story to tell. Bohm arrived at Birkbeck College in the University of London in the autumn of 1961. He was 43 years old. He had been in exile from the United States for 10 years. He had moved from Brazil to Israel to Bristol. And now, finally, he was in a city where he would stay for the rest of his life. Birkbeck is an evening college, an institution whose students work during the day and attend lectures at night. And Bohm's teaching schedule accordingly ran late. He often walked home through Hendon in the dark. He wore a long coat. He looked, to his colleagues, like an absent-minded professor from an earlier century, which, in a sense, he was. He had been formed in a world that no longer existed. The furniture store father, the science fiction magazines, the Berkeley Communist Study Group, the Princeton bow ties, and the Institute's private dining room. All of it had receded into a past so distant that when his American biographer, F. David Pete, visited him in the 1980s, Bohm would sometimes refer to events from the 1940s as though they had happened to a different person, which, in a way, they had. He married Sarah Wolfson, known to everyone as Saral, in Israel in 1956, and the marriage was, by every account available, the central stabilizing fact of his adult life. Saral was a sculptor. She understood him. She tolerated, which is saying something, the depressions. She brought him back from the edges he went to during his worst episodes. The marriage lasted 36 years. They had no children. The life in Hendon was quiet, domestic, undramatic. The research was monastic. Bohm worked with his small group of students and collaborators at Birkbeck, published steadily but not prolifically. Read the philosophers who interested him, and did not attend the international conferences he was not invited to. In 1959, he had, while still in Bristol, read a book by the Indian philosopher Jiddu Krishnamurti. The book was called The First and Last Freedom. What drew Bohm to it was a passage about the relationship between the observer and the observed. Bohm, who had spent a decade thinking about exactly that relationship in the context of quantum measurement, recognized something in the way Krishnamurti discussed it. He wrote in his later account, quote, "What particularly aroused my interest was his deep insight into the question of the observer and the observed. This question had long been close to the center of my own work as a theoretical physicist." Unquote. Bohm arranged to meet Krishnamurti. The meeting was in London, at the Sarnen gathering. At one early moment in the conversation, Bohm used the word totality, and Krishnamurti jumped up from his chair and embraced him. That was the beginning of a relationship that would last nearly a quarter of a century. Bohm and Krishnamurti recorded, over the course of their association, more than 144 dialogues. These are available in published form. They are long, sometimes rambling, sometimes brilliant, sometimes unreadable, but consistently characterized by a kind of patient circling around the questions Bohm had spent his scientific career pursuing. What is the relationship between thought and the thing thought about? What is the observer? Is there, or can there be, a pure observation unmediated by the concepts the observer brings to it? These questions, for Krishnamurti, were spiritual questions. For Bohm, they were extensions of the physics, the question of what it would mean to understand reality directly, rather than through the representations of it that our theories provide. He told Pete, at one point, quote, "I have seen some of the things Krishnamurti talks about. I have looked at reality and seen that it is an illusion." Unquote. I have had a complicated relationship with the Krishnamurti period in Bohm's life. Some of the physics community uses it to dismiss him. They say, well, the man went mystical at the end. Clearly his judgment cannot be trusted. Let us return to the serious scientific Bohm of 1952. This is, I think, uncharitable, in a way that misreads what Bohm was actually doing. He was trying, as serious people sometimes try, to find a framework in which the physics and the ordinary first-person experience of being conscious could be discussed together without either of them being reduced to the other. He did not become a guru. He continued publishing technical physics papers up through the end of his life. His last book, The Undivided Universe, co-authored with Basil Hiley and published posthumously in 1993 by Routledge, is as rigorous and unsparing a technical work as anything he had written in the 1950s. The Krishnamurti dialogues sat alongside the physics, not instead of it. They were, for Bohm, part of the same inquiry. Whether you agree with that choice or not, it is worth noting that the physicist most often accused of having gone soft is the one who, at the end of his life, produced an 800-page technical reconstruction of the ontology of quantum mechanics, while simultaneously conducting the most sustained public philosophical conversation of the 20th century. That is not a man losing his grip. That is a man who has decided that the grip is more important than the disciplinary boundary. The depression, though, was real. Bohm had struggled with it his entire adult life. His mother had been mentally ill. His childhood had been emotionally chaotic. He had the kind of mind that would not let him rest. And he had, since the 1950s, been carrying the accumulated weight of the exile, the professional erasure, the slow realization that the theory he had spent his career developing was not going to be accepted in his lifetime. By the late 1980s, the depressions were becoming more severe. In May of 1991, he confessed to Saral and to his longtime friend, the psychiatrist David Schoenberg, that he was feeling suicidal. He was admitted to the Maudsley Hospital in South London on May 10th of 1991. The medications did not work. After extended consultation between Saral, Schoenberg, and the treating team, they agreed to proceed with electroconvulsive therapy. Bohm received 14 bilateral ECT treatments. He was released at the end of August 1991. The depression appeared to lift, but, as Hailey would observe in later interviews, he was not the same. The memory loss that sometimes follows ECT was pronounced. He had lost, or at least had difficulty accessing, some of the physical intuitions that had been the core of his creative process. He did not have, as Hailey put it, the same energy with which to engage in our research in physics. The last year was productive nonetheless. He and Hailey were finishing The Undivided Universe. The book had been in preparation for decades. It was the attempt Bohm had been slowly making since the 1950s to write down in one place the ontological picture that the 1952 papers had left implicit. It contained the mathematical apparatus of pilot wave theory, the quantum potential, the guiding equation, the extension to quantum field theory, and a long conceptual discussion of what the formalism was describing. It was, in some ways, the book Bohm had been trying to write his entire life. He worked on it through the autumn of 1992. He seemed, by all accounts, to have stabilized. On the afternoon of October 27, 1992, Bohm was at Birkbeck putting finishing touches on the manuscript. At 6:15 in the evening, he telephoned Saral from his office. He told her he was about to leave for home. He added a final sentence in that phone call, the last sentence his wife would ever hear from him. He said, and this is from Pete's biography, quote, "You know, it's tantalizing. I feel I'm on the edge of something," unquote. Then he hung up. He put on his coat. He left the building. He got into a taxi. The taxi drove him through central London toward Hendon. Somewhere along the route, or perhaps only after the taxi had pulled up outside his home, he suffered a massive heart attack. By the time the driver understood what was happening, Bohm was dead. He was 74 years old. Hailey would speculate later, in interviews, about what Bohm might have been on the edge of. Their research, in the final months, had been moving in the direction of understanding the relationship between quantum processes and mind. They had been reading neuroscience together. They had been discussing whether the mathematics of the implicate order, the term Bohm used for the deeper structural level that the pilot wave formalism pointed toward, might bear on the question of how consciousness arises from physical processes. Hailey believed Bohm had seen something, some connection, some geometric or algebraic structure that tied the quantum formalism to cognition in a way that had not been made explicit before. Whatever it was not written down. The taxi drive home was not long. The notes Bohm had been making that afternoon, if there were such notes, were not preserved. The edge he was on vanished with him. I want to come back to the phone call, because the phone call is the part of the story I keep returning to, and I think it is the part that tells you what the whole story meant. It's tantalizing. I feel I'm on the edge of something. This is, in the ordinary course of a scientific life, not a remarkable thing to say. Scientists are on the edge of things all the time. They call their spouses. They mention the edge. The next morning, they come back to the office and they work out whether the edge was an edge or an illusion. And the research proceeds and the edge accumulates into a paper. What makes Bohm's phone call haunting is the knowledge that he had been on that edge, in some form, for 40 years, since 1952, since the publication of the 2 papers in Physical Review that had ended his American life. He had been standing at the edge of a worldview the profession had agreed not to look at. He had been telling Saral he was on the edge, and Sorel had been taking the call, and the world had been going on without listening. And then he said it one more time, into a phone, from an empty office at 7 in the evening on a Tuesday in October, and he put on his coat, and he went to the car, and the 40-year project ended not with a paper, but with a cardiac event. The Undivided Universe was published by Routledge the next year, highly completed the remaining work. The book has been quietly cited in the foundations of quantum mechanics literature for 32 years. It has never been a bestseller. Most of Bohm's obituaries in the general press focused on his connection to Krishnamurti. The New York Times obituary mentioned pilot wave theory in a single paragraph, deep in the body of the piece. The reader who came away from the obituary with the impression that David Bohm was a physicist turned mystic would not have been corrected by anything else the obituary contained. The man who had solved the measurement problem died with a paragraph of attention to the solution and a page and a half to the mystical dialogues. That is the distribution of attention the culture was prepared to allocate. And here is where we arrive at the place I have been trying to lead you to for 3 hours. Here is the implication that the 1952 papers, taken seriously, require you to sit with. I am going to say it as precisely as I can, and I am not going to soften it, and I am not going to pretend I have a comforting frame for it, because there is not one. If Bohm was right, and the evidence as I can read it says he was at minimum possibly right, and at maximum almost certainly right, then the universe is a fully deterministic system. The wave function of everything that exists evolves according to the Schrödinger equation. The particles in everything that exists follow definite trajectories guided by that wave function. There is no randomness. There is no genuine openness. There is no point at which the universe decides something new. The decisions were all made, if the word decision applies at all, at the moment the universe's initial conditions were set. Everything that has happened since, every galaxy forming, every star igniting, every life arising, every civilization rising and falling, every phone call you have ever made, and every thought you have ever had, was, in the relevant sense, already contained in those initial conditions, and in the wave function they evolved into. You are not an observer making choices in a live universe. You are a pattern of particles playing out a trajectory that was fixed before the Earth existed. The thought you are having, right now, in this precise second, about whether to accept this framing or to reject it, is a trajectory of ions moving through the neurons of your brain, and that trajectory, like every other physical trajectory in a Bohmian universe, was determined by the initial state. The feeling that you might have thought differently, that some other conclusion was open to you, is a product of your ignorance of your own initial conditions. It is not a feature of the underlying physics. The underlying physics is completely closed. It runs one way. The way it runs has been fixed for 13.8 billion years. Sitting inside this implication is uncomfortable, and the standard move when physicists get uncomfortable with an implication is to retreat to one of the other interpretations and pretend the implication does not apply. You can go to many worlds and say that the universe branches constantly, and that every possibility is realized in some branch, and that the feeling of making a choice is the experience of the branch you happen to be in. This does not restore your freedom, because you, specifically as an embodied sequence of brain states, are a particular branch, and that branch was going to be traversed in exactly the way it has been traversed. You can go to Copenhagen and say that the universe is fundamentally random, that particles do not have definite properties until you measure them, and that the universe is therefore an open system in which real novelty occurs at every moment. This does not restore your freedom either, because the randomness is genuinely random, meaning it is not under your control. And if your brain's behavior is driven by quantum randomness, then your choices are dictated by events that have no connection to you, your values, your character, or your reasoning. And that is worse than determinism, not better. You can go to the various consciousness-centric interpretations, the ones that say reality is produced by acts of observation, and you can convince yourself that your consciousness somehow does the observing that makes things real, and therefore that you are participating in the construction of the universe in some privileged way. This is, in my honest opinion, the interpretation that the popular physics community has been selling for 30 years, because it feels good, and it is the interpretation that the 2025 Nature Survey found is held by about 4% of professionals. Professionals know it is a fairy tale. The public has not been told. Bohm's theory, by comparison, is emotionally difficult but intellectually clean. It tells you what the wave function is. It tells you where the particles are. It tells you why experiments give the results they give. And it tells you, as a direct consequence of its honesty about these questions, that you are not what you thought you were. You are a pattern running in a larger pattern, and the larger pattern has been running itself out according to fixed laws since the first moment the laws came into being. Your sense of inwardness, your sense of deliberation, your sense that the next moment is undetermined until you act into it, is an artifact of being a pattern that is computing its own trajectory in real time from the inside. The feeling is real. The feeling is the experience of the computation, but the output of the computation was, in a sense that matters, set before the computation began. This is what Bohm saw. This is what the profession did not want to look at. This is why the 1952 papers for 73 years have been treated with the professional equivalent of a 1,000-yard stare, the eyes sliding past them on their way to the next equation. Einstein called it too cheap. What he meant was, at some level, that the theory was too successful at dissolving the mystery he had hoped would protect classical determinism from quantum randomness. Bohm's theory does not compromise between classical and quantum. It is classical through and through at the level of particles, and the only price it pays is the one price the universe actually demands, which is non-locality. And once you accept the price, you find yourself inside a universe that is closed in a way classical physics was too polite to be honest about. The Newtonian clockwork was deterministic in principle. The Bohmian universe is deterministic in practice, in every measurement, in every photon that reaches your eye, in every thought that crosses your mind. The clock does not just tick. The clock has already finished ticking, and you are experiencing the ticking from inside the mechanism. David Bohm died at 74 on a Tuesday evening in October of 1992 in a taxi in the north of London, 27 minutes after telling his wife on the phone that he felt he was on the edge of something. 40 years earlier, in January of 1952, the two papers had appeared in a journal he had been unable to attend the publication of in person, because the State Department of the country of his birth had taken away his travel documents at the instigation of a security apparatus that had decided his political history was unacceptable. Between the two dates, a discipline had elected, without anyone voting, to pretend the papers did not exist. The discipline was wrong to do so. The papers are correct in every way that can be tested, and they reveal In the structural features they imply for the physical world, a reality that is more closed and more finished than the discipline has been willing to admit. You were taught the open version of the universe. You were taught the story in which your consciousness matters, in which reality waits for you to look at it, in which the future is undetermined until the moment of your action. That is the story that was put on the cover of the textbook you might have read, and it is the story that the popular physics books have repeated for half a century. The story is not supported by the mathematics, in the formulation of the mathematics that actually solves the problems the other formulations cannot solve. In the formulation that works, the future is not waiting for you. The future is not waiting for anything. The wave function is evolving. The particles are following. The trajectories were set a long time ago. You are not choosing whether to accept this. You are a trajectory, and the trajectory is running, and somewhere in the architecture of that trajectory, which extends backward through every decision your ancestors made and every collision in the early universe that fixed the distribution of matter, was the specific arrangement that has produced this moment in which you are hearing these words and having the reaction you are having, which was also set. Bohm's last words to his wife were that he was on the edge of something. The edge was always there. He had lived his whole professional life on it. The people who should have been standing there with him had declined the invitation. They had declined because the edge is uncomfortable, and because looking over it costs you something you would rather not pay. I cannot tell you what Bohm would have seen if he had had another decade. I cannot tell you what the implicate order is, or whether it is a real feature of nature or a suggestive mathematical fiction. I can tell you what his 1952 papers tell you, because the papers are still in Physical Review Volume 85, and you can read them tonight if you want. They tell you that the universe has been running a trajectory for 13.8 billion years. They tell you that every particle in your body is on that trajectory. They tell you that the thought you're about to have in the next 3 seconds is already part of the trajectory. They tell you that you were not told this, not because it is wrong, but because the people who might have told you decided it was too uncomfortable to say out loud. The papers are in the library. The taxi has already arrived. Sarah hangs up the phone. The mathematics has always known where you would be, and we, who were told the comforting version, are left to sit with the version Bohm told Sarah 40 years into the edge, and then got into the car. It's tantalizing. I feel I'm on the edge of something. He was. He had been. He still is, for anyone willing to read what he wrote. And the edge, as it turns out, was the universe itself, running its single determined course, indifferent to whether anyone was willing to look.